All right, apparently we need a part 3 now because I ran out of time. So let's talk about the final steps of this, okay? So this was the other example they showed you, okay? X of t equals k times t cubed. All right, these would be all the mathematical steps of all of that drawn out. We don't have to do that. We are just going to go from here to here, okay? So in calculus class, I'm sure you're going to walk through all these steps. We are going to just start from here and go to here. So hopefully you're noticing something going on if you looked at those examples, okay? So this, taking the derivative of this tells us the instantaneous, whatever this is supposed to be, a position, a velocity, whatever rate of whatever this is. So for example, if they were looking for the instantaneous position at 2 seconds, okay, we would plug in our position here and it would be at 8 minutes, okay? The derivative tells us how our displacement changes as a function of time though. So the rate at which displacement changes is called velocity. We already talked about that a little bit. So we can use this now to figure out how fast it's going at this time interval, okay? So if we were looking at traveling at t equals 2 seconds, taking the derivative would tell us that this is 12 meters each second. That's the instantaneous velocity at time equals 2 seconds, okay? So let's look at the pattern, okay? So if we had done the previous example with kt squared, you basically take your exponent here, you multiply this whole quantity by that exponent, so 2 times k times t, okay? And then you subtract 1 from this power, okay? So you end up with 2t times 1, all right? K in this example is equal to a constant 1. That's where the k went here. If I do this with kt times 4, we would multiply this whole quantity by 4, subtract 1 from the 4, and we get 4t cubed, okay? If we do this with kt to the 5th power, we would multiply this whole quantity by 5, subtract 1 from the 5, and we get 5t to the 4th, okay? So we should have, forgive us, Mr. Guerreri, is that how you say his name, I hope? All right, so we are just going to do a shorthand. So if we have an equation for the position with respect to time as kt to the n power, remember k is just a constant, so if there was a number there, then that would be in place of t. Then the derivative is just this whole quantity right here multiplied by n, and then we just to reduce that power by 1. Okay, so here's some more examples. If the position of x with respect to time is 20 times t cubed, multiply the 20 by 3, which gets you 60, subtract 1 from the 3, which gets us t squared. Okay. If the position of x with respect to time is 5t cubed plus 6t plus 7, you just do that same thing, but you do it for each term. So this one becomes 3 times 5, subtract 1 from 3, so you get 15 times t squared. T to the first power, 1 times 6 gives you 6. 1 minus 1, it gives you 0. T to the 0 power, anything to the 0 power is just 1. So you end up with 6. Imagine we have t to the 0 power here, so we multiply this by 0, that term goes away, okay? And one final example, 2 times t to the 6th plus 7 times t to the 4th plus 4t plus 2. 6 times 2 is 12, 6 minus 1 is 5, so I get 12t to the 5th power plus 28t cubed. 4 times 7 is where we get the 28, 4 minus 1 is where we get the 3. And then 4t, it's t to the first power, so 1 times 4 is 4. T to the first power minus 1 gives us t to the 0 power. Anything to the 0 power is just 1. And then the 2 is times t to the 0 power, so the 2 goes away, okay? In calculus, this would be like your C term, okay? When we talk about going the other way, we'll talk about what those mean. These are common calculus derivative rules. We'll be practicing some of those later, but you don't need to worry